is complete.
All right, so for our final talk of the quarter, we have Justin who will be speaking on Hecke eigensheaves via chiral homology.
All right. Start out by outlining kind of the plan. So the first goal is to complete the contemporary account of what's in the Feigin-Frenkel book. So the idea is sort of using Feigin-Frenkel and localization construction, applying some kind of local to global homology construction. People get the quantized Hitchin system, which is this. So it's a homomorphism of associative algebras from local functions on functions like global opers on curve to global sections of the listed differential operators on BunG. So this is sort of what we want, and it's supposed to have two main properties, features. So one is that it quantizes the Hitchin system. In other words, it's compatible with kind of the illustrations on both sides. The associated graded Hitchin map. So I'm not really going to focus on this so much. I really am going to focus more on property 2, which is the compatibility with geometric topography. So I'm not going to say much. I mean, I won't say all about one really. Sort of because it's not so difficult once we've kind of done the construction. We'll do this sort of local to global construction, and then to get one, really all you have to do is kind of see that you say like everything, all the whole construction that I do will work kind of at the level of Reese algebras or filtered algebras or whatever. So there's sort of a parallel construction you can carry out, a local to global construction to get the Hitchin fibration, and these are sort of compatible. So it's just kind of tracing the constructions and keeping track of the filtrations, and there's not a whole lot else to say about it. So I'll sort of gloss over one. Also, we don't really use one in such a serious way. So what is this? The fact that it's a quantization of the Hitchin system, what it really buys you is, well, one thing you can do is you can prove that the Hecke eigensheaves you get are non-zero, which is nice, and then you can also prove that they're actually perverted sheaves. But again, these are kind of like, well, the fact that they're non-zero is very important. The fact that they're a perverted sheaf isn't sort of a nice property, but maybe sort of a secondary thing. But there are also other ways to prove these facts. So anyway, won't go into that. I'll focus on compatibility with Hecke because this is what we need to actually show that we get a Hecke eigensheaf, right? Yeah, just to, elaborate on that a little bit. Right, next, maybe we'll oper. Call it chi. I can define an object by taking this quantized Hitchin map. So another way to say with the quantized Hitchin map is it's an action of functions on global opers on the sheaf of critically twisted differential operators. Right. If you like, this is another way of writing this, right? It's endomorphisms of sheaf of differential operators as a unit. Right. Universal property of operators. So this is an action of this commutative algebra on the object on this object of and so in particular, if I have a character, right? By the way, this is happening scheme. I'll mention it before. If I have a K point of this happening scheme, in other words, character of this algebra, right? I can tensor up with that character using this action and get a D module. Okay, and so then this compatibility with geometric stocking implies that link chi is a Hecke eigensheaf. Eigenvalue is the G-check local system underlying chi. Has G-check local system with some additional structure, the oper structure. Okay, and that's whatever this compatibility with stocking means. I'll formulate it more precisely later. So not too hard to imagine what it is, but what it will buy you, right, is exactly the fact that this construction yields an Hecke. So in particular, this will give us a construction of Hecke eigensheafs for all local systems which admit a global oper structure. So that's kind of a shot of the then if whatever time we have at the end, also of all cuspidal Hecke eigensheafs, so including those which don't necessarily the eigenvalue the local system doesn't necessarily admit a global oper structure. This is something I talked about way back in the overview talk. Using the fundamental local equivalence at critical. Sketch a proof of the FLE or this construction of the FLE, and then explain how you can do a local to global construction, sort of analogous to this, but allowing the oper structure to have poles, and that'll allow us to get arbitrary cuspidal eigensheafs. Okay, any questions before I move on? Awesome. Okay. So I think this is the part of the Jones and Frenkel book that's probably hardest to understand what's going on. Is to repeat the local to global construction, like the confidence-based talk. So yeah, this what I'm about to say, it's stuff that I learned from mostly a lot of conversation with Sam Raskin. And it's probably pretty hard to actually extract from the book, but I think it's there morally in some sense. Okay, so we'll do some construction of factorization algebras, then I'll explain this little passage. So first I want to explain this concept of the center of a factorization algebra. Next, I'll start out with factorization algebra A over X, so just to kind of fix my conventions, compared to Lee's talk from last time. So what is a factorization algebra? Well, it's an object. It's a complex P modules on Ron space. This is an extra structure. An extra structure is sort of the factorization isomorphisms together with a compatible unital structure. Those are kind of the two big pieces of structures I'm talking about, always unital factorization algebras. But in particular, there's an underlying P module on Ron space. So I think the way that we stated things, the way that is written in Nick's notes from 2009 as well, you can also kind of forget the connection, talk about factorization algebras just living in quasi-coherent sheaves on Ron space. If you remember, it sort of automatically acquires a connection anyway, and I would rather just like take the connection as part of the data from the beginning, and then I don't have to worry about subtleties like, how canonical the connection is, the derived situation, and so on. So I'll just keep it there from the beginning. And as usual, and for me, everything is derived, but maybe it doesn't matter so much in this talk because most of the objects that we need will kind of be classical. So I'll try to be clear about that. All right, so how do we construct this center? Well, first of all, I need to kind of slightly enhance the definition of factorization module that was explained last time. So first of all, if I have a finite set I can define a category of factorization B modules over X to the I. Okay, so this is the DG category with an action of D modules on X to the I. Lives over X to the I duran. Let me say what an object is concretely. So I think the way that Lee stated it, I think he defined this in the case where I is a singleton, something like that. You can also fix a point on the curve and consider that sort of thing, right? But you can also allow arbitrary powers to the curve, which is what I have to do now. So concretely, object of this category is the following data. First of all, we're given an object of D module on marked Ron space. We explain what this means. Ron subscript I here is the following pre-stack slight variant of the Ron space. So it classifies, one way to say it, I guess, is it's a subset of the curve together with an I tuple of marked points. So I'll write this as a pair. X sub I is a point of X to the I. J, this is a script J. I'm just using a script here to distinguish it from like I is like some abstract indexing set, right? And then the script letter will indicate actually a subset of the curve. Okay. We differentiate between the index set and like the actual subset of the curve. So script J here is a finite subset, such that if I actually take a finite set of points, I get kind of, well, by considering this not like forgetting about the marking range, just considering this is a subset of X, it's actually contained in J. Okay, so again, just to repeat, this parameterizes a finite subset of the curve together with an I tuple of marked points contained in that subset. Okay. So if you like, you can also think about this as like this is like the datum of a map from I to script J. Right? Same thing? Okay. So, and then the other data, other main piece of data here is an isomorphism as follows. So I'll explain the symbols in just a second. So, oh yes, so we call this object M. My D module M. So it's an isomorphism like so. Okay, so where J and mu are as follows. So J is the inclusion of the disjoint locus inside of mon times Ron. Right, where the two finite sets don't meet. And then U is the kind of union map. It's like a natural semigroup structure on Ron, right? Just being like union of finite sets. Okay. Oh, sorry, I should have said one of these is the marked space, right? So sorry, it should. That would be the thing I wrote before would be like if you're defining factorization algebras or factorization modules, we're using kind of the if I union a finite subset and then a finite subset with an I-tuple of mark points, I get a finite subset with an I-tuple of mark points. Right? So that's what this, it's still kind of union, but I'm carrying along the structure of the mark points. And then this, again, this, like I said, where these two finite sets are. Okay. So if I start with M, I restrict it here, it should identify with a box type. Make sense? Okay. So like I said, this is just what Lee said in the case where I was a singleton. You know, and then there's kind of various compatibilities. So I don't have to spell out explicitly because I need to do it kind of carefully in unhomotypical ways, like a giant pain. It can be done. So compatible with the sort of usual factorization structure. A. And there's various higher compatibilities. I think you can, everything is sort of classical, like genuine D modules, like you can spell all this out explicitly as generally a little bit clever with how you do the homological theory. Okay, so that's factorization modules over power. A few comments about this. So x to the I sits inside this marked Ron space, right? So I have like a diagonal map, right? Close embedding, and in particular, I get a map. Sorry, I get a functor from factorization A modules on x to the I to D modules on x to the I, where I restrict, right, my M to x to the I. And there's sort of a funny psychological thing here, which is that you should really, even though like I said this first datum was a D module on marked Ron space, the underlying object of the factorization module you should really think is this guy. So like in the analogy with like E2 modules or E1 modules or something like that, this is actually the thing that's analogous to like the underlying vector space. And you should really think about this object M that lives on marked Ron space as being part of the data of the action, if that makes sense. Right? Because it kind of it looks like this over the discrete locus. So like it also sort of has a there as well. Right? Whereas this thing is sort of just that makes sense. So in particular, this this functor is conservative. You should really think about this as forgetting the factorization A module structure. Psychologically, this is a forgetful functor. Okay. And all of this kind of assembles into something over Ron space. Right, so I can take something that looks like a factorization A module over every x to the I, compatible under the diagonal restriction maps. Right, and so I can talk about factorization modules over Ron, okay? And this thing, well, for one thing, it has a forgetful functor to do modules on Ron space. Okay, I get by taking the limit of these guys. And also this has an action of D modules in the Ron space. So it sort of lives to Ron to Ron, right? Just like the individual powers over X and the other. Questions?
Good. You know if there would be like connecting the production, but this would be fiber function.
Fiber functor. I'm not sure what it means.
So that were analogy with vector spaces.
Yeah.
If that were some sort of functor
Like
to
that
that,
means-
could you be, like, is that somehow like analogous to Tanakian formalism kind of?
Well, no, it's more analogous to like if I forget the like if I have, so if A, for example, is an associative algebra, right, I can consider bimodules, which are E1 modules, and there's the forgetful functor from bimodules to the underlying vector space. It's analogous to that, really. Okay. Yeah, so it's more like that. So like, yeah. I'll leave it at that.
Case of modules, it doesn't like an abstraction.
I have what?
In the case of modules, it doesn't like it an abstraction. The module.
No, I don't think so, because for example, like the
You're taking that one, no, I get it.
yeah, but it's not going to reconstruction to work. You need the forgetful functor to preserve compact objects. Doesn't
What is it like? What do you mean by that?
like to if you want to prove your category is representations of a group scheme, group scheme or something. And this thing just would not be in general, nor would it be for like models, right? It wouldn't preserve.
No, it's more than
compacts in general. Yes, you'll be able to do the okay. Okay, so the first example of this, I'm looking at all this formalism for a reason. So the vacuum module over my factorization algebra A, it lives in A mod 1, right? And the point is kind of, if I forget the factorization A module structure on the vacuum, I just get the factorization algebra A itself, right? That's the underlying E module. On Ron is just A itself. So this thing is A as factorization module over its it's like the associative algebra is a bimodule over itself. It's completely analogous to this. Okay. And so what this allows me to do is define so-called center of this factorization algebra. So it's analogous to actual homology, right, for associative algebras, which is the endomorphisms of the associative algebra as a bimodule over itself. It's actual homology, right, for associative algebras. So for factorization algebras, we take endomorphisms of this vacuum module, okay, as a factorization A module. Okay, but I don't want to consider this as just an abstract like associative algebra. I actually want it to be a D module on Ron space as well. So I'm going to take inner endomorphisms with respect to the action of D modules on Ron on this category of factorization. So this is just like some general nonsense, right? If I have a monoidal category acting on some module category, and I have two objects of the module category, I can form relative inner hom, and it will live in the acting monoidal category, right? Just has that the obvious universal property. Hom n is given by the usual tensor Hom injection. Okay, so this will be an object. A priori, it's just an object in D modules on Ron space. But we can see that it has two additional pieces of structure. So in fact, well, first of all, it has an associative algebra structure that just comes from the fact that it's endomorphisms of something. Okay, So it's an associative algebra in D modules on Ron space, and here I'm just thinking about D modules as a symmetrical category under useful tensor products, quantized tensor product, right? So it's an associative algebra. Also, it has a factorization algebra structure in its own right. It comes from the factorization structure on the vacuum, which is just the factorization structure on A, really, right? So this thing is actually an associative algebra and a factorization algebra compatibly. So I can just package that by saying it's an associative algebra in the category of factorization algebras. Okay, so if you've ever thought about like Ian algebras, this kind of thing might look familiar, right? This is like saying if I have an E2 algebra, right, and I take this kind of E2 center of it, the thing that's analogous to actual homology for E2 algebras. So it's endomorphisms of A as an E2 module over itself. That thing is again an E2 algebra. It also has a commuting associative algebra structure because it's endomorphism to something. Therefore, by Dunn additivity, it's an E3 algebra. So this is like that type of thing. Okay. So for us in this situation, it's an associative algebra and factorization algebras. It need not be commutative. In fact, it essentially never will be if A is not trivial. Even if I start with a commutative algebra A, it typically won't be.
But like the global section.
Hmm?
At the end of the H0 global section.
Oh, like at a class, yeah, at the classical level, it would be it's won't be commutative because you can have kind of because of derived stuff basically. But how do you say like it's again it corresponds on under in the world of topology, it would correspond to the E3 algebra. So it's it's pretty commutative, but it's
global section will be the algebra.
well, I don't know what you mean by global sections. Like if like okay, so if A is classical, I take this thing, it need not be classical, then I take H0, it'll be.
Doesn't generalize the fact that the center of the vacuum was commutative, or it is going to be?
Yeah, so H0 is commutative, but as if I take like R ends, right, DG endomorphism is not actually going to be commutative at the derived level. Okay, just commutative at the classical level. Okay, but
A is trivial. What does this give you?
if A is trivial, then it will be trivial. Yeah. So it would be commutative in that case, but basically in no other cases. Like again, if A is commutative, this produces something typically not commutative. I mean, it's not that crazy. Like, think about another kind of analogous situation would be like the Drinfeld center of a nodal category, right? If I start with a symmetric nodal category and I take its Drinfeld center, I typically get something that's braided but not symmetric. It's that type of thing. Okay. So yes. Okay. So this is the type of object it is. Okay. So this is the center. So I'm going to use this in the construction, the global construction eventually. So before I do that, I need to do a digression on commutative factorization first. Okay, so we'll come back to this. But yeah, the example to keep in mind is where A is the vacuum, for the Kac-Moody algebra. Okay, and this thing will be sort of the endomorphisms of the vacuum that appears in Feigin-Frenkel, right? Or some drag version of it. H0 will be a thing. Okay. Great. So first of all, there's the two things I want to say about commutative factorization algebras. So one is that a commutative factorization algebra is position. I want to say this precisely. Let's an object of arbitrary is an object in the category of commutative factorization algebras, but in fact, it's a commutative algebra in the category of commutative factorization. Okay, so it's like this type of thing, right? It has a commutative algebra structure with respect to pointwise tensor product compatible with the factorization structure. This is not so weird if you think about just ordinary commutative algebras, right? Like category of commutative algebras in commutative algebras is again just commutative algebras. It's sort of like idempotent, right? With that type of thing. So in fact, I claim kind of the forgetful functor to commutative factorization algebras is equivalence. And this is really easy once we know this fact that we thankfully stated for us, which is that if I restrict from commutative factorization algebras, restrict them along the diagonal, right? So this is a D-modulo Ron space with some additional structure. I can restrict it to a D-modulo just on the curve X itself by restricting along the main diagonal. And that thing will carry then commutative algebra structure with respect to tensor product and D-modulos on X, and this functor is equivalence. So we kind of explain this at least for classical things. It's true in total generality.
So that's a D, not a NAPLA.
This is a D. Yeah. D-modulos on X. So just if I have, and remember these are, you can also think about these as at least if for the connected things, right? These are just like D schemes of affine D schemes over X. Right, the spectrum of such a thing will be an affine scheme over X with a connection, right? So, and then we also explained how you can construct the inverse geometrically by doing this kind of horizontal Jackson direction, right? To get a factorization space from a D scheme, and functions on that will be the corresponding commutative factorization. Okay, and the point is, right, now this is just literally a category of commutative algebras. So I can use the fact that I said a moment ago, which is that, like, what's the point of this? The point of this is that, like, the tensor product of commutative algebras is the co-product. Right? So, like, if I have a category with kind of finite co-products, then anything is canonically commutative algebra, the full map. Right? It's just this abstract nonsense. Okay, and then that proves it. As this functor is symmetric monoidal, obviously, because it's just given by restrictions over respect to tensor products. Okay. So this thing is also it's the category of commutative algebras. This thing is also just irregular. Okay, that was like that was very weird and abstract. I think it is. It's just an abstract nonsense. But it's okay, like a more kind of down to earth interpretation. It's related to the thing that we explained last time about how if I have a factorization algebra that has kind of a commutative associative algebra structure and it's classical, then that has to be commutative. Okay, this is kind of related to that, right? So this is saying something slightly different, but closely related, which is if I have a commutative factorization algebra, it's canonically a commutative algebra with respect to pointless problem. So in particular, it follows if I have such a commutative factorization algebra, again, canonically has a commutative algebra expressed with respect to pointwise tensor product, and I can then forget, right, to first of all just associative algebras. Then I can forget from commutative factorization algebras to just arbitrary factorization algebras. Forget the commutativity of both types of algebra structure here. And so such a commutative factorization algebra determines the same kind of objects, right, that the central is. I can forget the commutativity. So commutative factorization algebra, in particular the factorization algebra, and it's canonically a commutative algebra with respect to pointwise tensor product, therefore it's also canonically associative algebra, just like pointwise tensor product. Let me just take a moment. I know it's a little psychologically challenging, if not mathematically challenging. So pause for a second to internalize this and see if you have questions. Okay. Great. The other thing that I want to say about commutative algebras is well, it's kind of redundant actually after what we explained last time, but this idea will be useful to us anyway. So the chiral model.
You expect me to the first line again? Why that you have that isomorphism?
Yeah, because this is the category of commutative algebras in a set of categories. Therefore, like the tensor product computes the co-product. Okay. And if I have a co-Cartesian symmetric normal category, the forgetful functor from like commutative monoids to the underlying category is equivalence. It's just this stupid thing, right? Like if I have every object has kind of a canonical commutative algebra structure, which is the whole thing. Yeah. This is something you can do in any category of commutative algebras because tensor product is the co-product. It's just some kind of slightly mind-bending like Hecke. Takes a little bit of thought. Okay, so the proposition I want to state is that, well, this is a commutative factorization algebra, in particular it's a factorization algebra. I can take its chiral homology, which remember is just the flat sections on the round space, right? And I claim that this is naturally a commutative algebra. It's a natural commutative algebra structure. This is in contrast with just the chiral homology of a general factorization algebra, which is only a vector space, right? But I claim if I start with the commutative factorization algebra, the chiral homology is canonically a commutative algebra. Now, we already said last time, we have an explicit formula, in fact, for this chiral homology, namely its functions on the kind of space of flat sections of spec B over X, right? Okay, so a posteriori, we know it's a commutative algebra anyway, but this is something kind of more direct and elementary. And then you can state Lee's theorem as like you have an isomorphism of commutative algebras, right? Where this is kind of the a priori commutative algebra structure on chiral homology. That makes sense. So I don't have to use Lee's theorems. So the proof, well, let me actually deduce it from the following lemma. Which is that the chiral homology functor from the chiral homology functor just as a functor from factorization algebras to vector spaces, I claim is actually symmetrical. This is not obvious. And in fact, if I just took abstract D modules on Milan, right, which chiral homology technically is defined on such things, right? Because I can take their flat sections, but this wouldn't be true, right? Just like you don't expect, if I have some, say I had some like proper variety, you wouldn't expect the flat sections functor to preserve this, right? Generally, there'll be like a map in one direction, but it won't be nice, right? This will be sort of complex. So this is something kind of special in factorization algebras. Although that's maybe overstating the case slightly, but what actually matters here is the unital structure. So all you really need for this to be true is that you start with the D module on Ron space that has kind of a unital structure. It doesn't need the factorization isomorphism, it just need the unital structure, and then you'll if I tensor two such things, take their homology, it'll be the tensor product of the chiral homology.
That like so we take like the categorical occurrence, the category of subsets, same thing, so we will get.
Yeah, so right. So the unital structure would be like upgrading into a D module on the kind of unital Ron space. Yeah, exactly. And I can either take kind of flat sections on unital Ron space or flat sections on ordinary Ron space. It gives the same result. Okay, so I'll just kind of sketch the proof. Ultimately, I'll have to reference something kind of slightly non-trivial, or at least don't go into the board. So remember how this chiral homology construction works. I've already said it out loud, right? First, you forget to just the D module, the underlying D module on Ron space, and then you take sort of Durand homology on Ron, right? So, of course, Oppler is symmetric monoidal. That's just the definition of the tensor product of factor. The tensor product of factorization algebra is just pointwise, right? So that's trivial. The interesting thing though is C rem. So the rem homology function is a priori op-lax or left-lax symmetric monoidal. Namely,
They're not homology, right?
rem homology, although it doesn't matter because it's kind of improper. But it's the same as homology.
But the homology is always the right left.
Left lax. Homology is left joint to something symmetrical.
So homology is right left.
Homology is left. Lower tree, right?
Oh, you just say the homology.
Lower. No, it's upper shriek at the left joint is homology. Homology is not right joint, right? There's no upper sliders. It's just it's right joint. It's kind of the upper shriek pullback from a point, which is symmetric monoidal. Right, so homology is not priori left-lax symmetric monoidal, but okay, in fact, it is strictly symmetric monoidal. So you have kind of a map in one direction from the chiral homology of the tensor product to the tensor product of the chiral homologies, and I claim that's an isomorphism if I plug in unital sheaves on Ron space. In particular, if I start with unital factorization. And the reference for this is kind of updated version of mixed thesis, called like connection by model space, blah, blah, blah. And I won't take the first, but I'll just say look there, and it's one of these kind of contractibility statements for Ron space. But I think the formal statement is the diagonal map of the unital Ron space is universally homologically cofinite. Okay, whatever. Check out next paper if you want to understand that in detail. But anyway, this is kind of a nice, this is, to me is a little surprising, or at least I forgotten about it for a long time before I prepared this talk and then remembered. So very nice. And now the proposition, right, which is it just follows immediately from the lemma together with this fact, right? Right, so start with the commutative factorization algebra. It's canonically a commutative algebra under pointwise tensor product, but chiral homology preserves the pointwise tensor product since it's a tensor product. So again, okay. That's why I really needed it to be strictly symmetric monoidal. Ob-lax means you preserve coalgebras, but I really wanted to preserve algebras. So didn't need that. So now I come to the main kind of local to global construction. Combining all the previous ingredients. So we're going to start with A and B as above. We're going to A in factorization algebra. The commutative factorization algebra. And again, this is a proposition, but maybe it's like, I guess you could have said this about the previous two, but it's sort of proposition construction. Doing a construction rather than stating a fact. So if I give myself the following data. A homomorphism from B to the center of A, and I want it to be in this category of, it's a homomorphism of associative algebras with respect to pointwise tensor product, and it's also compatible with factorization. It lives in this context. Okay. So you can, I don't know what to call this, central homomorphism from B to A or something like that. So it makes sense by everything I've already said, right? And the claim is that this gives rise to, squiggly arrows when I'm saying this is a construction, an action, okay, of the chiral homology of B, which is a commutative algebra, on the chiral homology of A, which is just a vector space. So now this is like the main construction of today's talk. Follow pretty easily from what I've already done. Questions about the statement? So I guess like this would still be valid, even if B was just a priori like an object in this category, it can still work, but it needs to be compressed. Okay, so a morphism of this form, it means in particular that B acts on A just in the symmetric monodal category of demodulable on space. Right? Remember, this is like inner endomorphisms of A with respect to back in this category. So just kind of by the tensor homojunction, giving a homomorphism like this is, well, in particular, it's giving an action like this. I'm forgetting about the fact that it's also compatible with the factorization A module structure. Okay, but in particular, I get an action just in this symmetric category. This is a commutative algebra there. This is an object there, so this makes sense. Okay, so in particular, let me just kind of be a little bit loose here. Just say I have an action map like this, right? Inside D modules on Ron space. And now take chiral homology. Take flat sections on Ron, right? And again, well, the point is just this symmetric modality of chiral homology, right? So I have like a map like this that's actually an isomorphism. Because these are factorization algorithms proceeding over there. Okay, so this will be the action map. Again, the fact that this is symmetric modal on factorization algebras is going to tell me that I actually get an action like so. Totally fine. Okay. So, yeah, so this limit was really crucial. It's okay. Okay, again, kind of the main construction. Questions about that? Let's see how this gets us at least part of the way to what we want. With size, this is the Feigin-Frenkel situation.
Having just a map B to A is not enough to get.
No, we want B to act on the vacuum module. That's really the data. Because A doesn't like act on its vacuum module in any meaningful sense. Right? Just like in the context of E1 algebra is like A doesn't act on itself as a bimodule of itself. Because it doesn't, like if I take left multiplication, it doesn't commute the bimodule structures. Yeah. Okay, so the key example for us, right? We're going to take A to be the kind of Kac-Moody chiral algebra at critical level. I'm just going to freely use this passage between chiral algebras and factorization algebras that we talked about. They're the same thing.
And B is going to be the commutative algebra attached to the D scheme of opers on the disk. Okay, hopefully it's kind of clear what I mean by this.
Isn't that exactly the same?
Sorry?
That's not exactly the same.
You're asking like if this is going to be an isomorphism?
Yeah.
It'll be an isomorphism on H0. But
Oh,
yeah. Yeah. We're actually not going to use the fact that it's isomorphism on H0. For the same thing. Okay. So let me just comment on what happens when you take chiral homology of these things first. So first for A, let me just take kind of the untwisted version for simplicity, because the twist just adds some additional notational headache that I don't want to deal with. So let's just say, first of all, you know, if I don't do a twist, right, this is just the chiral enveloping algebra of this least star algebra G censored out with differential operators, right, by definition. Okay, so as we explained, there's a formula for chiral homology of such a chiral enveloping algebra. Namely, it's the Chevalier-Eilenberg complex alias Lie algebra homology of the following DG Lie algebra. It's the Gram homology on X of the Lie star algebra that assembles into a DG Lie algebra, and then I can take its Chevalier-Eilenberg complex. It's Lie algebra homology. So this is the Bell's-Drinfeld formula for chiral homology of a chiral enveloping. This is Chevalier-Eilenberg. Sorry, I know there's a lot of C's. Yeah, it's I don't know what else to call it. It's really just a random. Sorry, Lie algebra homology. So this DD. Okay, we can spell out this is a little bit further. So first of all, if I take the Ram homology of G tensor D, right? Well, this is like D module induction of G tensor O, and then I take Durand homology of it. So that's the same thing as doing R gamma on X of G tensor O. That's sort of the compatibility of induction and D module push form, right? And so this thing is well, it is what it is, but kind of by some I don't know, Spencer deformation theory stuff. This is exactly the fiber of differential operators on BunG at the trivial G. Okay, so hopefully, you know, you can kind of believe something like this. So
The Schritt fiber, like that's what you mean.
sorry?
You mean it's the Schritt fiber?
Schritt fiber.
Yeah.
What's the difference between Schritt fiber and ordinary fiber?
Schritt fiber is the ordinary fiber. I mean, there is no star fiber for something like differential operators. I mean, it would be dual to the Schritt fiber, so it would be the. Generally speaking, if I'm on like, let's say I'm on a smooth line, right? The Schritt fiber of differential operators is a point, as are the kind of formal distributions supported at that point. The dual of that would be the completed ring of functions, right? So the Schritt fiber is the one that really genuinely exists, like a discrete vector space. The star fiber will be something like a topological vector space. So this is also the one if I forget the D module structure and just go to an O module and then take the kind of fiber level of quasi-coherent sheaves, it's the same thing. So this is really the canonical one. So again, this is very closely related to the fact that this DG Lie algebra shifted by, let's say that this DG Lie algebra shifted by 1 is the tangent space of BunG at the trivial D model. Okay, so there's some kind of general yoga to go from kind of that description of the DG Lie algebra that controls the deformation theory. The Chevalier-Eilenberg complex of it will be the distributions form at that point. Okay, I'm not really going to, well, I'm not going to use this directly, but this is kind of just a plausibility. Convince you that this has something to do with differential operators on BunG. And then you can do the same, you can do a twisted version of this. I won't go into detail on, but if I do this with the twisted version, with respect to some level, I'll get the kind of fiber twisted Hitchin operators. It's kind of twisted show out. Like that. Right, and as for B, and we stated this last time, by the formula for chiral homology of commutative factorization algebra, which is going to be functions on global numbers, because this is exactly right the space of horizontal sections of this DC. By definition. Okay, so I'm saying this is a theorem, but it's a big thing. All right, so sort of an upgraded version of Feigin-Frenkel. Unfortunately, don't have data. We were kind of discussing like, what extent does it follow from the Feigin-Frenkel that we stated. It's not too far from it. The main thing is just checking compatibility factorization, which is something we've got something extra to do. So it's exactly a homomorphism of this type. Again, I'm not even using the fact that it's nice. You know, I mean, although I think somehow that's how it's constructed, I guess. Like you somehow explicitly calculate that H0 of this thing is this classical algebra. You get all the points. So you have to do this in such a way that it's compatible with factorization. So be like, I don't know, could be a nice project for a grad student or like an undergrad. No, I mean, because it's just really like it's mostly there. It's just like this extra ingredient of doing it carefully so that you get the factorization structure.
A really, really strong high school.
Yeah, it's really, really strong. Okay, so this is kind of the datum that we would want from Feigin-Frenkel, and then the construction, the proposition construction over there, right, is going to give us an action of functions on global opers on the chiral homology of A. A, which again is this fiber critically twisted differential operators at the trivial level. Okay, so this is not quite what we wanted, right? There's two things that we still need to do. One is to go from an action just on the fiber of the trivial G bundle to an object, to an action on the entire object. And then the other is compatibility with society. About.
Can I ask?
Yes.
Is there a way to get like any fiber of differential operators if you like modify A?
Yeah, absolutely. I mean, you can kind of twist everything by arbitrary G1, produce a similar formula. I'll sort of comment on this when I talk about this. Yeah, you can totally generalize this, and that's going to be dangerous. Yeah. So we kind of also want action of functions on global opers on the entire sheaf of differential operators and not just the fiber at an individual point. And then of course we still have the compatibility of society, which is going to come somehow from some compatibility of this with Satake and then a local different structure. Questions? Okay, I think it's probably time to break, right? Sweet. All right. So at this point, localization is going to first appearance. As I said in the abstract, like the key idea here is that localization should be thought of as some kind of enhanced form of chiral homology. I mean, I guess I should say. Okay, yeah. So I don't mean that in like too broad of a sense, but just like Kac-Moody localization can be carried out over the Ron space, and when done so, it can be interpreted as kind of like upgraded or enriched form of homology. So then previously constructed localization functor. Take this as my input. Look of G coming up, happen to be any level, first Russell one should be critical. And this goes from from the Kac-Moody representations, which are integrable for our group. So Chandra modules, right? Over the entire Ron space. So again, you can kind of interpret this by the limit formula that I wrote earlier. We sort of know what these things are over a power of the curve. We can also do it over the entire Ron space all at once. For example, the vacuum module itself, factorization algebra, it has a life of a Ron space, right? And these things localize onto BunG. Generally, you get counter twisted A modules and okay, so I'm going to take this as my input. Although actually, yeah, let me actually say what we're calling construction. So think about full push along a certain correspondence. Yes, it's in the sense that games go up to reality, right? So on the one hand, we have sort of the classifying pre-stack of this Chandra pair. Seems kind of like an unreadable mess, but hopefully people. Okay, so this is like a group, right? It lives over Ron to Rom, and I can take its kind of classifying pre-stack.
So what is the subscript? What's that like? No, but the subscript about
The subscript, it's just saying it's like relative to this is a group over Ron to Rom. So I'm taking this classifying pre-stack is going to also put
Oh, no, but I mean on the other side. The
this.
L plus G.
Oh, sorry, that's R group. L plus G. So it's the completion of the loop group along the R group. Remember, this is like the formal, this is the group whose representations are modules over the Harsh.
Okay, I try to see it.
If I have a group and a subgroup, I can take the formal completion along the subgroup, and representations of that thing will be it's sort of the exponential of the Harsh, right? Okay, so info on this thing is exactly this category up to the twisting that I'm ignoring in some places, right? And upstairs, well, let me first write over here, right? I'm going to have, of course, BunG for them. This is where D much on BunG live. And then what's upstairs? Well, I have this pre-stack. actually, I guess, the scheme. But I want to kind of allow the point at which I take the level structure to move. So this is going to be something that lives over Ron space, right? And it's like I give myself a finite subset of X, I give myself a G bundle, and I take a trivialization along the formal completion of X of that finite subset. Okay, and that thing is acted on by the loop group. In particular, it's acted on by this formal completion. And then again, just to emphasize, this whole thing lives over Ron space. So again, this is a reminder from Kevin's talk. I'm not sure how much I'll actually need it, so don't sweat it too much. But this is how the localization is defined. Fits into some kind of general yoga. I have kind of a hard Chandra pair acting on the scheme or stack or whatever. Then I can do this kind of localization construction. Okay. I think the only thing that here that wasn't emphasized in Kevin's talk quite as much is that like you can do this over x to the I for any I, you can do it over the entire Ron space, works just as well. Just keep in mind here when you do this push forward, right? This thing kind of lives over Ron to Rom. So when you're doing this push forward, like imagine, for example, if G was the trivial group, right? These would both be a copy of Ron to Rom. And this would be a point, and then here you'd be taking chiral. So this push forward operation is involved in chiral. So that's what I'm going to kind of comment on now. The Durham pre-stack Ron space. So like the thing intco on that thing, or the deco is debunked. Okay. So full push, there's some infinite dimensional subtleties that I'm ignoring. With Capit's list and some infinite dimensional subtleties, both of which I'm ignoring. Important here. So I won't need this formula, so maybe I won't prove it, but let me just state it kind of for psychological reasons. So if I take some object of this category, okay, and localize it, and then I take the fiber at the trivial G bundle, I claim this is simply the chiral homology of the underlying demodular Ron space, underlying factorization. Is so forget the fact that it was a Kac-Moody representation, right? It's the demodular Ron space. I can take its chiral homology. So I claim that the fibers of localization, when I do it over the entire Ron space, are actually computed by chiral homologies. And you can also write down kind of an analogous formula for the fiber at any point, and you'll get some sort of twisted version of A here.
Oh, you read it, sorry.
I don't remember what.
The twisted version of A.
Yeah, so, oh, and I guess, sorry, just before this does use, sorry, this isn't quite for any arbitrary, for any object of equity representation of a Ron. It's, you also need the kind of universal structure. So let me just say for simplicity, if A is a factorization algebra, kind of in this capitalistic. But you really just need the universal structure that's used here. We'll only apply it to the vacuum. So, sorry, so the twisting, the interesting thing is, so this formula, if you think about it, it doesn't actually use the action of the Lie algebra at all. It only uses the action of the arc group. So I can actually write the same formula for just any representation of the arc group over Ron space. And if I have a representation of the arc group over Ron space, and I have a G bundle, I can twist it by the G. Okay, you just think about it, there's kind of one formula that you could possibly write down using the associated bundle construction. Okay, and that'll be a demodular Ron space, and you can take its column. Yep. So this I won't give the proof in detail, but it can kind of be extracted from paper of Rosenblum's that I mentioned earlier. Again, it's so sort of what's going on here is, like I said, this formula for the fibers, it only depends on sort of the underlying L plus G representation, and what the action of G hat kappa of the Kac-Moody algebra is giving you is somehow it's determining the connection, the kappa twisted connection to this localization as the debug varies. Okay. So if you look at this correspondence, right, what if I just replace this formal completion with just L plus G itself, right? Then the quotient at the top would just be BunG times run, right? There'd be no connection on BunG. But when I further mod out by the formal completion of the loop group along the arc group, that's kind of what's going to be allowing me to produce some loop connection. Okay, so you can kind of contemplate this formula and stronger and stronger variance. I don't think I'll use it directly.
Like,
Sorry?
is it equivalent, like giving a connection along one same extent?
Yeah, in a sense. This is kind of like the main theorem of this paper by results. So yeah, you can. If you say it correctly, then it's true. You have to say it's kind of like giving the action kind of over the entire space. So you really have to do it for all on because it really uses contraction in a serious way. Okay. All right, so let me just write down a couple of things in this verbally on board. So as an exercise, you can formulate and improve similar formula for the fiber of localization at an arbitrary. All right, so now what we're actually going to use, so it's morally related to this, only maybe not. Not used directly. I'll use a sort of compatibility of compatibility of this localization bunker with chiral homology in the following sense. Let me state it as concretely as possible. So let's take A is going to be a factorization algebra in Kac-Moody representation, and the Kac-Moody category. The B is going to be just plain commutative factorization algebra. And the claim is that so again, this is in particular a D-module Ron space, right? I can tensor it with A, and I get another object of the Kac-Moody category. Okay. D tensor A, I'm just again viewing it as an object of this category. I can localize it. And the claim is that this is actually isomorphic to the chiral homology of B tensored with localization. You can see it's kind of a compatibility of the action of Ron space on this category with the localization functor and the chiral. Okay. So the proof, I'll just say it's very similar to the proof that chiral homology is symmetric. You know, I only sketched that proof, right? So you can go back and look at it, and it's going to use the same ideas. And again,
So that man Ekman helped it.
it's and it's only really using the fact that these are unital. I don't really need the factorization structure. It does use the unital structure. Well, it's not really Ekman-Hilton. It's really it's again this kind of universal homological cofinality.
So
For the
E2,
overall space.
E3.
It's more about like contractibility.
I see.
Again, if you look at Nick's paper, again, look at the recent version from 2021, and just Control F, like universally homologically cofinal or something like that. You'll find these
Sorry, I missed that, like B is completely federation of in like finalistic category or
just an abstract unit factorization.
oh and
Yeah.
Like you did write it.
It's connections on moduli spaces and infinitesimal Hecke symmetries or something like that. It's the kind of like cleaned up like Lucy version of this basically. Okay. It's very, very nicely written and easy to read, so you can find a lot of this stuff. Okay. So for us, like B is going to be function numbers. Again, same notation. Okay, so now in this situation, right, where I have this kind of Kac-Moody symmetry, and I'm doing this in some slight inverse generality I need, but A is ultimately going to be the vacuum for us. I can define this center. I'm going to use the same notation, even though it's just ever so slightly different from what I wrote before. But this is kind of internal to Kac-Moody representations, to the cosmologistic category. So I write the same formula as before, but now I take factorization A modules. It's a factorization of algebra in this factorization category, so I can take factorization A modules in this. I take inner endomorphisms as such. Again, kind of with respect to the action of the modules on the run space. And this is not going to be a very serious distinction for us because A will be the vacuum. And so this category will actually just again be the Kac-Moody category of Kac-Moody representations. Like this won't do anything because this is going to be kind of the unit. So the only thing that's different from the way I wrote the center before is that we're taking endomorphisms in this category where I have the L plus G into the middle. That's not a big difference. So you can mostly ignore small difference between this and the previous formula. And again, this is just going to be an associative algebra in factorization. Okay. And now, again, B is included in factorization algebra. A continues to be a factorization algebra in the cosmologistic category, and I'm given a homomorphism as before. This proposition, if you apply the same construction I did before, and use this proposition, you'll get an action of the commutative algebra given by the chiral homology of B on the localization of A. Again, just to remind you, this is an object in characteristic D modules on BunG. You kind of imagine how this linearity gives you this demonstration, right? Okay, great. So that actually takes care of the first desideratum from before, right? So this is going to give us an action. Just writing out explicitly. in our situation. This spits out action of functions on global opers on critically twisted modules, critically twisted differential operators. Because this is exactly the localization at critical level of the vacuum Kac-Moody localization. That was like part of the package of localization. The vacuum localizes to different operators. So this recovers the action from before when I take the final. Use this formula, right? Questions about that? Okay, so the last thing is compatibility with system. Okay. So for this, I need to talk a little bit about the factorization space of the local system. I need to talk about, Satake factorizably. And here I mean like just the kind of abelian categorical Satake, not anything derived, but I do need to kind of compatible with factorization. So look at the category of representations and I'll create group P. This G is going to be used to check later, but check now. It's a symmetric modal category. Therefore, there's some general yoga that allows you to produce a factorization category from it. This is kind of the analog of the fact that in E-infinity algebra is in particular E2 algebra. There's some algebraic construction that allows you to do this, something totally categorical. There's also a really nice geometric construction, which I'll explain now. So I'm going to define a pre-stack it's going to be a factorization pre-stack of local systems on the disk. Okay. Actually, I could just write some very compact formula, which is like it's horizontal jets into point mod G. But let me actually write it a bit more explicitly as a moduli space. So it's first of all, this version lives over x to the I, the rem. So it's going to consist of an I point of, sorry, let me do it, yeah, again for with testing S. So the S point of x to the I is rem, right? So this is an I tuple of F reduced points of x, right? And then also a G local system on the formal multi-disk at xi. Okay, so what does that look like explicitly? Well, here's the formal multi-disk. Okay, this is like the formal completion of the graph, right, of these points. I take the rem restack. Okay, but now here's something slightly funny that happens. I don't want to say I have a map from this into point mod G, because that would also give me a connection along S. But this should be something like a map from S times D to RAM to point mod G, right? It should not come with a connection along S. Okay, and so I do the following thing. I take fiber product over S RAM with S, and then my G local system is going to be a map from this into
So that stops. It's a flat in the direction X.
yeah, it's flat only in the X direction, not
Okay.
the S direction. Yeah, exactly. So if you think about what you would do for the global curve, right? Like locus G of X, an S point would be a map from X to RAM times S to point mod G. Right. This is the local analog of that. Again, this is just like by definition, this is horizontal jets into point mod G as a constant. Okay, so in particular, the fiber of this thing at an individual point is well, it's a local system on the disk, which is going to be trivial. Right, so just a copy of the classifying stack. So this thing, like over a set of disjoint points, it looks like a product of copies of the classifying stack. And in particular, unlike the sort of situation that you see with like the Eigenvalue, for example, this thing is not locally defined. Just pointing that out, again, I'm not going to emphasize these issues, but it's worth contemplating. I mean, it's, as I've said before, when you have a factorization space with finite dimensional fibers, it really cannot be, it's just never going to be locally defined type. This is a funny sort of space where if fibers over x to the I, the base is finite type, the fibers are finite type, but the total space is not. Very weird. You don't see that very often. Okay.
That is great. No, that's completely nuts.
It's
Where
funny.
does the extra? Where does the extra?
There's some really simple example of this would be something like the following. So generically, it looks like A1 times A1 minus 0, right? If I localize X, if I invert X, so if I take X equals 0, I just get a point.
You did.
Right, because if X equals 0, you can easily prove Y also. So that's a case where, you know, upper semi continuity is violated, the dimension jumps down. There's no contradiction there because that thing on the right is obviously not finite type. So it's this, that type of behavior. Okay, so now the factorization category of G representations, I'll just define it by taking quasi-co on factorization space of local systems. Okay. And so again, this thing is going to have fibers that look like rep G or tensor product copies of rep G, right? It's going to factorize. And in particular, I can do this thing on the whole run space. Well, that's the limit, right? The categories of rows to the I for all I, or I can also say it's quasi-co of the version of this over the entire run space. Either way. So this will allow us to talk about factorization algebras with a compatible G action. I think physicists call this gauge symmetry. Kac-Moody symmetry, which is what we talked about before. Okay. So now there's an analog of localization in this situation. I'll call it loc G infinity. It really is localization at infinite level in a precise sense. And it goes from rep G1 to quasi-co looks this G on the global. Okay, so namely, we pull push along the correspondence, just like we did for Kac-Moody localization. It's the following correspondence. The geometry looks maybe a bit simpler, so so this map is restriction from global local system to local system on the disk. And if I have a local system on X in particular, I get a local system on any multi-disk. I just need pointing on in the codomain here for this to make sense. Or sorry, in the domain. And then this is the projection of ports. Pull push, again, we kind of see chiral homology because it's projection. An important point is that this functor is actually a localization in the sense of category theory. Definitely not something that happens at other levels, right? So this is due to Kac squared and Larry, at least that's who Nick attributes it to. So this G infinity admits a continuous and fully faithful right adjoint. It's also given by pull push in the opposite direction in the appropriate sense. Okay. I won't give the proof, but I'll refer you to any of. Actually, I think the place I know of where this is written down, it's probably written down in other places, but it's definitely written down in the notes from the workshop in Jerusalem. Just notes by Nick on like global constructions or something like that. Also a good source for this material. It's a lot of overlap in the state as well. Okay. Again, it has something to do with contractibility of the Ron space. Also, you have to use something like this calculation of chiral homology and commutative algebra. Those are the ingredients. Another fact that I'll use about this is that this loc G infinity is symmetric monoidal, at least on unital sheets. So just going with my previous convention, I'll just go ahead and say for factorization algebras. So if I have two objects that are unital with so objects in rep G Ron that have a unital structure, in particular, if they're unital factorization algebras that would work, then local preserve their tensor. So proof is, again, I'll just use this in weasel words, similar to the proof that chiral homology is unital sheets. Let's have some basic facts that go into it. Okay, and then finally, I want to explain. So I said this is obviously reminiscent of chiral homology. There's some chiral homology happening here because I'm taking a direct image of something. It's like Ron to Ron. I can say something more precise. So let's suppose we're given for a moment, I'm going to say this. Yeah, so B is we commutative algebra and rep G. I'm going to say this. No, sorry, I want to say, sorry, B is just a commutative algebra in D modules on X, or equivalently a commutative factorization algebra, just like it has all along, right? And suppose we are given also map from spec B to point line G. Okay, so it has a life over the classifying stack. Okay, so notice this is kind of the same thing, right, as giving a G courser. Equivalently, I give myself a G courser, which is also going to be affine. So let me call it spec B enhanced. Right, getting a map to the classifying stack like this is the same thing as giving a G courser over stack. right? It will also be affine because G is affine. So this is going to be a G torster. And notice, by the way, that the reason I'm calling it B enhanced is because it's going to be a commutative algebra in rep G over X. And it's going to have the property that kind of, when I take the G invariance, I recover B. So it's a kind of G equivariant upgrade of B. You should be thinking about the case where B is inverse, right? And it lives over locus G on the disk. Okay, so then I can give a formula for, I can give a compatibility between this locus G infinity and chiral homology as follows. So again, this is a commutative algebra in rep Gx. By the same kind of yoga as always, I can think of it also as a commutative factorization algebra in rep G, right? And in particular, I can apply this locus G infinity to it. And the claim is that if I take global sections on locus of the localization of this B enhanced, that's going to canonically identify with chiral homology. So notice the difference between this compatibility and the earlier compatibility of localization. Before, the compatibility for Kac-Moody was that the fiber of localization at a G bundle could be expressed in terms of chiral homology. Now the compatibility is that global sections of this localization can be expressed as chiral homologies. What's a bit different? Okay. So, and I'll just say I won't really give a detailed proof, but just as kind of a sketch. The point is that, again, spec B kind of lives over point mod G. So in particular, it lives over locus G on the curve. I mean, this is just concretely, this is just like X and mod G. Okay, so the spec B lives over that thing. And then when I take flat sections over X, right, I get exactly this chiral homology of B by the formula for chiral homology of the commutative thing. Spec of that. And flat sections of this is just going to be locus on the global curve, and well, this gets you most of the way there. It'll live over locus. Okay, so again, I'm just sketching it. Again, you can get these ideas. You can get the more detailed proofs from mixed papers, but notice when I take, like, I can take functions on this, and I can consider it as a quasi-coherent sheaf on locus G by taking direct image. Global sections of that will just be this space of functions. So, okay, so that's slightly hand wavy, but basically proof. Okay, so let's we should have called that section something else, but anyway, factorizable stockade. Stated like this. I guess but be careful, it's critically twisted. This spherical category, and it's pretty common notation. So hopefully you remember from my talk, my first thought, right? This is like L plus G equivariant D modules of the FN Riemannian, right? Or D modules of the Hecke stack. Okay, then do a critical twist. So we're wrong. Okay. And so geometric Satake, I claim, can be made compatible with factorization in this sense. And for a careful proof, you can look at Sam Raskin's paper, chiral principal series categories 1. It's like section 6 or something like that, called Around Factorizing Satake, where he explains this carefully. And you can basically deduce it from like the way that it's proved in your conventional owner. It's not too far to get to this. Okay, and then in particular, the spherical category over Ron, the critical level, is going to act on the cosmological category. As I think we've hopefully previously discussed, it's really just because this is how much the invariance of something. In the sense of like strong actions grouped by category, so there's some formal thing you can deduce it from. It's a sort of convolution action. Okay, so in particular, we get this action of rep-g check on the cosmological level, and it's compatible with factorization. So I'm going to do one more iteration of this center construction. So again, A is a factorization algebra in the cosmological category at critical level. And I can define what I'll call like the enhanced center. So it's the same kind of enhanced as like the de-enhanced notation from before. So it's going to be very similar kind of formula. Relative inner endomorphisms in the category of factorization A modules, which are also the cosmological category. It's relative inner hom with respect to the action now of rep-g check on. So the only difference from the previous formula is before I wrote D modules on Ron, here I'm writing rep-g check. Okay, so I'm using this action instead of the action of just plain D modules. So this thing will live in associative algebras, in factorization algebras, in rep-g check. So it's the same kind of thing as before, but now it also has this G check case. And kind of by construction, it's going to have the feature that if I sort of, again, this is sort of a G check representation. If I take its G check invariance, I'll get the previous center. So this is kind of a G check equivariant operator. Makes sense? Now we want to do the global construction. So we need the following pair of case stories, which I alluded to but didn't quite state, I think, in my first talk, which is the action of rep-g check Ron on D modules on Ron's on BunG. So this category acts on your critically twisted D modules on BunG. It's the Hecke action kind of over the entire Ron space. So I get an action of rep-g check Ron on this category. And the claim is that this factors through low-g check infinity. So in other words, it factors through an action of quasi-co looks this on the board. Very useful to remember here that this functor has a fully faithful right adjoint. So this statement is really a statement, it's really a condition and not a additional structure to give this factorization, because all I have to prove is that this action, the objects in the kernel of this functor act by 0. Then I'll get this factorization. So that's what Kac-Moody did. This is in this paper, generalized vanishing theorem, something. Okay, so this gives the so-called like global Hecke action rank of this category on critically twisted D-modules on BunG. Okay, so that's all the preparation. Now here's the construction. We're going to rerun the same construction we did before one more time, but now with the Hecke action present. So suppose we're given, B/B enhanced as before. So spec B lives over point on G, or over Loxus G on the disk, right? And suppose we're given homomorphism from B enhanced to this enhanced center of A. A is the same thing. This has been here. Okay. And again, this is going to live in associative algebras, in factorization algebras, in Rich. Okay. So further enhanced version of see that as before. We combine all the constructions from before, and we get the following. So first of all, I can do this localization at infinity to be enhanced. So this is going to be something that lives in quasi-code Loxus G check, and it'll actually be a commutative algebra, right? Because I proved that this functor is, or stated that this functor is symmetric monoidal on factorization. This will map to the following thing: relative inner endomorphisms for the action of quasi-code Loxus G check on critically twisted D modules on BunG of log G crit of A. Okay, so this is what, if you carry out the same construction I wrote before, but like bringing along this Hecke action, okay, just combining all of the ingredients, this is what it spits out. Now, this is very hard to parse for me. Let me just say where this lives. This lives in commutative algebras, or sorry, not commutative. The right-hand side is not commutative necessarily. In associative algebras, in quasi-code Loxus G check. Okay, I personally find this formula, this kind of thing, very hard to parse. So let me just say it slightly differently in a way that I think is more intelligible. Equivalently, what this produces, the functor from conformal blocks, chiral homology of B, commutative algebra, I can take modules over it, to critically twisted B modules on BunG. And this functor is going to send this commutative algebra as a module over itself to differential operators. And it's going to be equivariant for the action of quasi-code Loxus. Okay, so by this formula, right? stack of this commutative algebra lives over locus G check. So the left-hand side has an action of this category. The right-hand side has an action by the Gibbs vanishing theorem. And this is going to be equivariant for this action. That's what the global construction implies. So this is the same datum. Is this homomorphism? Hopefully you agree with me that this is a little bit easier to understand. You see why this is the same kind of datum? Because to give a functor out of a category of modules is equivalent to just giving an action of the commutative algebra itself on wherever it gets sent. Okay, so if I in a functor that sends this to differential operators, this is giving an action of this commutative algebra on this object. And then all this business about intermittent morphisms, and this localization at infinity, this gets packaged up in the equivariance of this functor of this action, this global action. Class, it's probably pretty transparent how we apply this in our case. Let me just write it down really quickly. So A is the vacuum Kac-Moody representation. B is functions on the disk. Get is a functor quasi-co of global opers to P modules of G that sends the structure sheet to differential operators, and it's equivariant for the action of this category, where the action on the right side is by Hitchin's theorem, and the action on the left side is just because Oper's not teleposts. This is what I promised, right? That's this equivariance is the global Hecke. Okay, so I'm already over time. I did promise this thing about opers with poles. I could do like a really kind of quick like blitz version of that if you guys are interested. Sure. Is that okay? Okay, so let's take a few minutes to say you work about that quick version.
We're not going to time 3 minutes here.
Yeah, okay, great. So as we'll do this because I promised it the first talk. So fire. I guess what I'll skip is the constructor of the FLA critical level because it's sort of secondary, but it's not directly relevant here, but we'll talk about it some other time. So actually first, yeah. So remember the other character that appeared when we were talking about this FLA critical level, it's the following thing. So I called it like opers unramified local. Okay, so this is the following thing. It's and it lives over wrong. It's the following thing. So it's opers on the puncture disk together with an extension of the underlying local system. Maybe let me just erase the Ron and just say everything here is referring to Ron or XXVI or whatever you like. Together with an extension of the underlying local system to the disk. Or kind of symmetrically, it's a local system on the disk together with an oper structure on the function disk. Okay? And this is a factorization space. In particular, there's a version of it that lives over Rondo. It's all these things in addition. Okay. And notice also that it's projects the locus G on the disk. So it's going to have an action of redshift. Well, quasi-variant sheaves on it will have an action of redshift. Okay, so critical level FLE. Equivalence of factorization categories. The listed category at critical level with info on the unramified local inverse. We also want compatibility with Sakaki, of course. So that we can encapsulate by just saying it's equivariant. This is still part of the statement of the theorem. Equivariant for the action of ret through check. Okay, so it acts on the left-hand side by Satake, as I explained before, and it acts on the right side because this local unramified opers projects the locus G on the disk. Okay, so that's the Satake compatibility. Let me just say really quickly verbally how you construct this functor. We'll use this operation called Drinfeld-Sokolov reduction. So if I have a Kac-Moody representation, there's this operation called semi-infinite homology. So it's an infinite dimensional version of Lie algebra cohomology or homology. Sometimes it's a combination of both. So what you do is you take your Kac-Moody representation, you restrict to loops of the nilpotent radical, okay, and you take semi-infinite homology against a kind of non-degenerate character of that thing. Non-degenerate in the appropriate sense, it's this Whittaker kind of stuff, right? So this produces some complex of vector spaces, right? Just some Lie algebra homology space, some complex of vector spaces. And then, okay, there's a sort of variance of Feigin-Frenkel that was proved by, I believe, Bellson and Bernstein, which says that semi-infinite homology can be identified with functions on local opers. So in other words, you can see immediately that it has an action of functions on local opers just by functoriality. Sorry, I should say I'm applying that semi-infinite homology Drinfeld-Sokolov reduction construction to the vacuum, right? So functions on local opers acts on the vacuum. When I take the Drinfeld-Sokolov reduction, it's going to act on that vector space, and the claim is that it's sort of a free module. Okay. It's kind of similar to how if you do like Whittaker reduction of the universal enveloping algebra in the finite dimensional case, it's a free module of one over this kind of thing. Okay. And so this is going to give you a functor from this category to sort of factorization modules over functions on local opers, and you can use that to map into this category by some, that's the construction. The reference for this is the extremely long paper by Shannon, Gates, Corey, and Raskin that is part of the proof. They give a proof there. This theorem. Raskin, although I would call it sketch. I think there's some details that are out there. Okay. And remember what we're supposed to have. A commutative square as follows. So this critical level FLE let's check. Okay. So this critical level FLE is supposed to be compatible with the language equivalence in the following sense. So conditional on geometric alignments, global geometric alignments conjecture, right? That's supposed to identify this category with intco with some single support condition on locus G check. And this square is supposed to be here. This is localization. Critical level. And this is pull push along a certain correspondence that I wrote in my first talk. So the right vertical functor will push along correspondence. So it goes this. So I have ramified local opers here, and I have global locis here, and then upstairs I'll have this thing that I call ramified global opers. So just to remind you, this was opers on the punctured disk. Well, just write the formula. I guess probably the most economical way to say it is I give myself a global G-check local system together with an oper structure at on the punctured disk at several points. Right. So this thing is overrun. Okay, so we do this pull push. And this is supposed to commute. So, you know, in view of this, it's sort of you can sort of see where you can get Hecke eigensheaves. So what's supposed to happen here? So Hecke eigensheaves are correspond to skyscraper sheaves on locus, right? So if I can lift, if I start with some irreducible G-check local system, say, and I can lift it to an unramified global oper, which I know that I can do conjecturally in all cases, and we know it definitely the G has connected center by the standard of Rankin, right? Then I could take the kind of skyscraper here, right? And I could do direct image, okay? So because this functor is given by kind of like pull push, well, we expect this composite to factor through direct image from here to here, okay? And if we knew that, then we could just say, you know, fix my irreducible local system, choose some kind of oper structure with poles, take the skyscraper sheet with that guy, and then apply this direct image. Okay. And so in fact, we can prove this factorization unconditionally. Okay, and then I'll stop. Sorry, I'm way over time. Wrap it up here. Okay, so consider the composition intco on ramified local opers. I do the inverse of FLE, so I'm really using the fact that there's equivalence here to get to Kac-Moody representations. Have the loosely category at critical level. It's wrong. And then localize. Okay. And this functor, right, because FLE is compatible with Kac, and because localization is certainly compatible with you know, the action of the spherical category. So this is equivariant to the action of rep G check over Ron space. But remember, the action of rep G check over Ron factors through this global Hecke action, right, on frequency D modules on BunG. And so what this tells us is that this functor factors through the following thing. Opers. Factors through the following tensor product. So here I want to take quasi-co, locus G check. And actually I want to keep a copy of Ron here, for reasons that will hopefully be clear in just a moment. But if this acting factors all the way through here, then in particular it factors through like locus times 1, right? Because that was an intermediate step. Okay, and so this functor will factor through this tensor product to give me a functor like so. But now look at this tensor product. Okay, so if you believe, under kind of very, very mild hypotheses, we expect like the tensor product of quasi-co to be quasi-co of the fiber products. This is int-co, but it's not such a big deal because the thing is normally smooth. So kind of ignore that. So this then, at least morally, should be quasi-co on a fiber product. And what is the fiber product here? The fiber product of this over locus G check on the disk with this. Yeah, it's exactly this guy. Maybe this should have stuck. Matter actually. No. Yeah, you can do it.
Is there a pithy name for that?
There is a pithy name. It's exactly info or quasi-co. I'm kind of working at that level of detail at this point. Unramified. So this gives the kind of factorization. Okay. So we get this functor from int-co on unramified global opers to critically twisted modules on BunG. And again, morally, it's given by just, it's supposed to correspond to Langland's duality by direct image along this map. But the compatibility, so this is going to be compatible with the action quasi-co locus G check on the global curve. Construction, right? I'm exactly using the escape for advantage theorem here. And it's going to be compatible with the action of this guy. And that's exactly going to tell you that if I start with a skyscraper sheaf here, and I apply this functor, which I'll call this extremely souped up version of the quantized Hitchin system, that'll produce a Hecke eigensheaf whose eigenvalue is the underlying G check. That's the description. All right, that's it.
Yeah. And so I'm not if there's like it was monodromy. We operate.
Say it means unramified.
Oh, it's
Yeah. So some people call it monodromy free, some people call it unramified. It's the same thing. Either one is kind of, it means that the local system has the overstructure. Okay. Any more questions?
Yeah, I would have thought that the thing right forward. Local system of X with the overstructure away from the point.
Yeah, you're right. Yeah.
Like X circle.
Yeah, you're definitely right. But yeah, this is a good point. So Dennis calls this sometimes like X minus. And the question is, does that completely break this argument? certainly less clear than I made it out to be, right? I have faith that there's something like this is true, right? It's sort of, it's like we were previously discussing. I mean, it's very close. This category is very close to taking like the unital subcategory of this factorization category, right? So I'm trying to do something like that, but also kind of quotiented by this functor, right? It should produce something. So again, there's a squiggly arrow here. There's a squiggly equivalence here. Okay, so what I want to say is that these are quite close. And yeah, maybe if even a better way to say it would be just to use this sort of unitality type argument. So somehow what this gate square vanishing theorem is buying you is that this factorizes through kind of the unital category of this thing, while simultaneously also kind of factoring through like the action factors through here. And so that should give you something like a functor out of, if not this guy exactly, then kind of the rational version of it, right? I have like a G-check local system on the global curve together with a rational oper structure. Okay, so yeah, maybe this version is there's some discrepancy here, but probably you can also phrase it in that way, and that would give you the same result as far as eigensheaves, right? So yeah, great point. So there's some ambiguity there. Yeah. Thanks.
You're wrong.
Here, yeah. Yeah, exactly. I was trying to do something over a functor out of something over Ron, but what I was saying is there's also kind of variants of this where you integrate over Ron space, and that'll produce something like instead of an oper structure with kind of labeled poles given by a point in the Ron space, it would be sort of indeterminate poles, just a rational oper structure, right? Where we use this usual kind of like equivalence relation on rational data. If this doesn't quite work the way I said it, then that version should have work. Okay, very much a sketch, so it would be a cool thing for somebody to write up, but
Is there a guess of what happens if you restrict like simple poles?
you restrict to simple
Like
poles.
You said these opers have poles. Like what if they just have block poles?
Yeah, I don't really have a good sense of, so again, what you need to construct Hecke eigensheaves is something along the lines of any irreducible G-check local system admits a rational structure. And first of all, I'm not entirely sure what it means for the oper structure to have simple poles, but yeah, I don't have a sense of how much you can control those poles if that's true.
Wait, regular singularity.
We're not talking about singular divisible local system, we're talking about singular divisible local structure, right? Yeah. Maybe you can say something about simple poles, but I don't see any reason why you'd be able to control the order of the poles, right? Another kind of interesting aspect of this is that you should also be able to do something for irreducible local systems. Like this is conjecturally just circular. Well, I don't think it's known outside of the irreducible case, and even for SL2, I don't think it's known for irreducible. So you can also use this to produce Hecke eigensheaves corresponding to reducible local systems. On the other hand, you can use geometric Eisenstein series to produce Hecke eigensheaves for reducible local systems. And so I think kind of the predicted compatibilities of geometric line ones would tell you that those things are not actually the same. If you remember, I gave this argument for uniqueness, like conditional on geometric line lengths. You expect Hecke eigensheaves to be unique if they correspond to cuspidal local systems, but otherwise the category of Hecke eigensheaves at a reducible local system is not in fact it's something you can describe, but it looks like something to do with singular support. It's not that. So it's kind of an interesting question to relate those precisely. I know it's something Dennis has thought about before. He spoke about it at some point in geometric lines office hours a long time ago, and I don't think the recording is this version of this. But yeah, it's kind of another interesting aspect of this.
Any more questions? So your speaker.